Hi, I'm Linda from English Learning Mind Map. Today, we will learn about neuromorphic computing. Neuromorphic computing. To emulate cognition and transcend bottlenecks through neuromorphic computing, we are building chips that think like humans. Basically, we are making hardware that copies the brain instead of just doing math. Synaptic Engineering. As a core pillar of neuromorphic computing, synaptic engineering allows us to replicate connectivity and optimize signaling. In simple terms, we are making the wires inside the chip act like the connections in your head. Plasticity Modulation. Plasticity modulation is a specialized branch of synaptic engineering used to adjust strength and enable adaptation within the system. This means the connections get stronger or weaker depending on how much they are used. Hebbian Learning. A key technique within plasticity modulation is Hebbian Learning, which helps to reinforce paths and solidify memory. To put it simply, we are making sure the chip remembers things better the more it practices them. Axonal Mapping. Axonal mapping serves as a practical application of synaptic engineering to direct impulses and minimize latency. Essentially, we are laying out the chip's internal highways so signals don't get lost or take too long. Signal routing. Within the scope of axonal mapping, we focus on signal routing to navigate data and bypass traffic efficiently. In other words, we are giving the electrical pulses a GPS so they can find the quickest way to the next neuron. Spiking neural networks. Spiking neural networks are an essential component of neuromorphic computing designed to utilize pulses and conserve power. Simply put, the chip only uses electricity when it has something to say, saving a lot of energy. Temporal encoding. Temporal encoding is a functional layer of spiking neural networks that helps to time events and represent data. This means the rhythm of the electrical bursts carries the message, not just the power level. Pulse width modulation. To enhance temporal encoding, we use pulse width modulation to vary signals and convey meaning. At its core, we change how long a blink of electricity lasts to send different codes to the machine. Event-driven processing. Event-driven processing is a vital aspect of spiking neural networks used to trigger actions and ignore idle components. Basically, parts of the brain chip stay asleep until they are actually needed for a task. Asynchronous logic. Under the umbrella of event-driven processing, asynchronous logic helps to remove clocks and operate independently. In short, every part of the chip starts working as soon as it's ready, rather than waiting for a beat. Memristive Systems. Memristive systems are a critical requirement for neuromorphic computing to retain states and integrate functions. Effectively, we are combining the hard drive and the processor into one single, tiny piece. Non-Volatile Storage. Non-volatile storage is a strategy within Memristive systems used to store permanently and survive power-off events. This means the chip doesn't forget everything when you pull the plug, just like your own brain. Resistance switching. By utilizing resistance switching within our storage, we can toggle bits and stabilize data. To put it simply, we change how hard it is for electricity to pass through a wire to save a piece of information. Analog computation. Analog computation is a technical application of Memristive systems to process ranges and mimic biology. In simple terms, the chip can think in shades of gray instead of just black and white. Continuous gradient. To refine analog computation, we use a continuous gradient to smooth transitions and handle nuance. This means the computer can understand things that are mostly true or a little bit of something. Cognitive architecture. Cognitive architecture is a fundamental goal of neuromorphic computing to synthesize logic and simulate mind. Basically, we are drawing the map of how the whole artificial brain should work together. Pattern recognition. Pattern recognition is a core part of cognitive architecture used to identify shapes and categorize input. This allows the machine to look at a messy picture and instantly know what it is looking at. Feature extraction. Through feature extraction within our recognition systems, we can isolate traits and ignore noise. In other words, the chip ignores the blurry background and only looks at the important stuff, like a person's eyes. Autonomous reasoning. Autonomous reasoning is a practical goal of cognitive architecture used to solve puzzles and infer meaning without help. We want the chip to be able to make its own decisions based on what it has learned. Self-directed learning. To support autonomous reasoning, we develop self-directed learning to explore options and improve alone. To put it simply, the computer goes to school by itself and learns from its own mistakes. Thanks for watching. Please like and subscribe for more English lessons.